Hello everyone, we will welcome to this video. We will proceed with the material of electrochemistry and hopefully that you will enjoy this video. In this video we'll talk about the oxidation numbers and let's go. So a quick recall before starting talking about the oxidation numbers. You just have to mention an important notion is when you still remember that when in the first video we talked about the Zn is becoming Zn2 plus 2 electrons, and Cu2 plus when is gaining 2 electrons to become Cu, and this formed the redox reaction, which was Zn plus Cu2 plus is giving us Zn2 plus, right, plus Cu. You still remember that we dipped zinc strips inside Cu2 plus ions, and then we get the Cu copper metals were formed, and that's why we concluded that the Zn loses electrons and undergoes oxidation, and Cu gained electrons and undergoes reduction, and we say that the electrons were transferred from Zn to Cu2 plus, right? And we mentioned that the redox reaction is the overall reaction where it shows where it's the addition actually of the oxidation half reaction with the reduction half reaction. When we add these two half reactions together, we form the redox reaction. And we talked about that redox reactions mainly involves the transfer of electrons from one chemical species to another. We will be under this umbrella, under this huge umbrella of redox reactions, but now we will talk about the transfer of electrons from one chemical species to another, but now the chemical species are becoming more complex. I mean, the chemical species are not so easily, we can really guess it easily. For example, if you have a reaction which is Cr2O7 2 minus is being added to Fe2 plus, this is giving us Cr3 plus Fe3 plus. Okay, now now we have the chemical species. Too many atoms and too many elements are being involved in one chemical species. Let's say that Cr2O7 2 minus are becoming Cr3 plus. Now it's really hard to guess whether this element is losing or gaining electrons. This element is undergoing oxidation or reduction, and for this reason, we will talk about the oxidation number. Oxidation number is something that we invoked in order to understand the oxidation reduction process inside chemical species which are complex, such as Cr2O7 2 minus. So let's proceed. So the objectives of this video, you will perform a number of dry reactions, right? We will talk about the dry redox reaction that we will talk about is magnesium. It is the combustion of magnesium. We'll talk about it, and we will understand that this is a redox reaction. The combustion of magnesium is actually a redox reaction. We will define the oxidation numbers of an element, and then we will apply the oxidation number of an element, and we will notice why the main usage of the oxidation numbers in the redox reactions. What do we mean? What do we care about having oxidation numbers in order to conclude if the reaction is redox or not? Okay. So first thing is we will talk about the dry redox couples and dry redox reaction. We have the combustion of magnesium. Mg is added to plus half O2 is giving us MgO. If you want just to have to look better, so we have Mg, 2Mg plus O2 is giving us 2MgO. So when we burn magnesium solids or magnesium wires, then we get a white powder, white precipitate, and this is MgO. And we wanted to discuss whether this is a redox reaction or not. Before starting discussing whether this is a redox reaction or not, we have to mention that Mg is a neutral atom, O2 or oxygen here is a neutral atom, so the charge is equal to the zero charge, and we will have zero charge. Now if we want to dissect MgO, MgO contains Mg2 plus and O2 minus. MgO mainly, if we want to dissect MgO, contains Mg2 plus and O2 minus. And then we can say that Mg here becomes Mg2 plus and O becomes O2 minus. It's obvious that here we have a neutral charge, then it becomes a positively charged. This means that there is a loss of electrons. Mg lose 2 electrons to give it to oxygen, which gain 2 electrons, if you can see this. Okay, so this it loses 2 electrons, so it undergoes oxidation. And this one undergoes reduction. Oxygen undergoes reduction because it gains 2 electrons. It was in neutral, then it becomes negatively charged, so it gains 2 electrons. Now, can we comment whether this is a redox reaction or not? Yes, it is a redox reaction because we have the transfer of electrons from Mg to oxygen. Although it's not clear to see it as the previous ones, but yes, this is a redox reaction. Why we call it why it's redox reaction? Because due to the previous interpretation. Why we call it a dry redox reaction? Because we don't need it's done in the absence of water. We don't need water to perform this reaction, and that's why we call it a dry redox reaction. So what are oxidation numbers? Why we need oxidation numbers? And what is the reason behind having to start with the oxidation numbers? As I've mentioned before, we had simple reactions. We had Zn is becoming Zn2 plus 2 electrons. Cu2 plus is gaining 2 electrons to become Cu. It was really simple. The redox reaction was simple. Now we're talking more of complex redox reactions. The elements are not, the chemical species are not elements anymore. They are molecular compounds. We have compounds that are losing electrons or gaining electrons, so it's really hard to guess whether this compound is losing or gaining electrons. And as I've mentioned in the introduction, that let's say if we have Cr2 O7 2 minus is becoming Cr3 plus, how can we notice that if the chromium here gain 2 electrons or lose 2 electrons? So it's really hard for us to notice, to guess if the one chemical species is gaining or losing 2 electrons. And so that it's really hard for us to comment if there is an oxidation or reduction reaction. So it's really hard for us to comment whether this reaction is redox or not, because we need to know if there is oxidation and reduction half reactions so that to comment that there is redox. For this reason, we invoked some arbitrary numbers in order to understand more about in order to track the electrons if are being lost or gained in a chemical species, and the movement of electrons. We invoke this arbitrary numbers in order to understand or to track down the movement of electrons from one chemical species to another. And it's really related to the electronegativity of an element. The oxidation numbers is related to the electronegativity of an element. Electronegativity of an element is the capability of atoms to attract electrons more than other elements. Like, let's say if we have the oxygen has electronegativity, higher electronegativity than nitrogen, then in forming covalent bond, oxygen can attract electrons more than nitrogen. That's what we say, that's what we mean by the electronegativity of an element. So the study, what's oxidation number? The study of redox reactions involving molecular compounds, more compounds, show that it's necessary to relate the notion of oxidation number to the electronegativity of an element. Oxidation number is written in integer numbers. And we will talk about how to calculate the oxidation numbers, and then we will move out to apply the oxidation numbers. So first, how to calculate the oxidation numbers. The oxidation number of an atom in its elemental form is equals to 0. Examples: Fe, H2, O2. The oxidation number of hydrogen in H2 is equals to 0. The oxidation number of oxygen in O2 is equals to 0. The oxidation number of iron in Fe, which is iron, is equals to 0. But if I have CO2, the oxidation number of carbon in C is not equal to 0. The oxidation of oxygen in CO2 is not equal to 0. We need to have like the same element. If you have a compound, we need to have it's to be consistent, or yani, we need to have the same element. It should be consist of the same element, like hydrogen and hydrogen. It shouldn't be H2O. So if we want to say that H2O, the oxidation number of hydrogen in H2O is not equal to 0. This is the oxidation number of H is not equal to 0 in H2O, but the oxidation number of H in H2 is equals to 0. So as I've mentioned, the oxidation number of an atom in its elemental form is equals to 0. The second rule is the oxidation number of monoatomic ion is equals to the charge of the ion. It should be monoatomic. Example, Mg 2 plus, Na plus, O2 minus, Cl minus. Here we said the oxidation number of oxygen in O2 minus is equals to minus 2. It's equals to the charge of the ion. It's equals to minus 2. The oxidation number of magnesium in Mg2 plus is equals to plus 2. The oxidation number of sodium in Na plus is equals to plus 1. The oxidation number of chlorine in Cl minus is equals to minus 1. So this is how we calculate the oxidation number of monoatomic ions. It's always equals to the charge of this ion. It should be monoatomic, okay? It should be consisting of one ion, of one atom, okay? So that if I want to calculate the oxidation number of Cr2O7 minus, then if I want to calculate the oxidation number of Cr, it's not equals to minus 2, okay? It's not equals to minus 2. Oxidation number of Cr is not equals to minus 2 because we have here many atoms. It should be one atom, okay? It should be monoatomic. Now, the oxidation number of an element, of an atom, of an element in a covalent molecule is equal to the charge conventionally attributed to the element in the molecule, okay? For example, H2O. The oxidation number here of H is equal to plus 1 because, why? Because when forming the covalent bond, okay, when forming this covalent bond, when forming covalent bond, H is 2H plus O2 minus. So here, the oxidation number of H is equals to plus 1. The oxidation number of oxygen is equals to minus 2. And we can give it a rule. Whenever we have oxygen or hydrogen inside, okay, inside a compound, inside a molecule, the oxidation number of hydrogen is plus 1. This is a rule. And the oxidation number of oxygen is equals to minus 2. This is for hydrogen. This is for oxygen. We have a special case, especially in H2O2. Special case. In H2O2, oxidation number of oxygen is equals to minus 1. This is a special case. Okay? So the oxidation number of hydrogen is equals to plus 1. Oxidation number of oxygen is equals to minus 2. Now, in a molecular species, the sum of oxidation numbers of all atoms is equals to the charge carried by this species. How? We have NH3, let's say. The charge of NH3 is equals to 0. As I've mentioned, plus 3, the oxidation number of hydrogen is equals always to plus 1. We have 3 hydrogens, so multiply it by 3. We don't know the oxidation number of nitrogen, but it should be X plus 3. This should be equals to 0 because it's a neutral atom. Now, let's say that we have HO minus, okay? The oxidation number of hydrogen, as I mentioned, is equal to plus 1. The oxidation number of oxygen is minus 2. And plus 1 -2 is equals to -1. Let's say I don't know here what is the oxidation numbers of hydrogen and oxygen, but I know the charge of this molecule. So I say this must be, the negative charge must be equals to the sum of oxidation numbers inside the atom. Okay, I'm just gonna give here an example of Cr2O7 2-. Here we have Cr2O7 2-. Okay, we have the negative charge, the 2 electrons, the 2- is going for the whole chemical species. I don't know what's the oxidation number of Cr, so I'm gonna have it as X, but I know the oxidation number of oxygen is -2. I'm gonna multiply -2 by 7 because I have 7 oxygens, and I'm gonna multiply X by 2 because I have 2 chromium. Then this is equals to what? This addition is equals to -2 because the Cr2O7 2-, the charge here is equals to -2. So this is -2. Okay. So if I want to calculate for Cr, so I have 2x minus 14 is equals to -2. Then I have 2x is equals to 14 over 2. 12. So x is equals to 6. This is how we are able to solve the oxidation number of Cr. So this is the last rule in molecular species. The sum of oxidation numbers of all atoms is equals to the charge carried by the species. Okay. Let's have few applications. We need to calculate the oxidation number of nitrogen in the following compounds. So in NO is a neutral, X minus 2 equals to 0. Then X, the oxidation number, when I say X, I mean the oxidation number of nitrogen. The oxidation number of nitrogen is equals to 2. The other example is NO2, nitrogen dioxide. Here we have the X minus 2 is the oxidation number of oxygen, multiplied by 2 because I have 2 oxygens is equals to 0. Then here the oxidation of nitrogen is X is equals to plus 4. Now this is a little bit challenging because we need to dissect here these 2 electrons. This molecule, this is NH4 plus and O3 minus. We need to dissect these two, this molecule into the equation of dissociation reaction. So this compound is ionic, and we need to dissect it in order to calculate the nitrogen here. So the oxidation number of nitrogen in NH4 plus, we have X plus 4 hydrogen. The one hydrogen is equals to plus 1 is equals to what? What's the charge here is equals to plus 1. So X here is equals to 1 minus 4. X is equals to minus 3. And in NO3 minus, we have X plus minus 2 multiplied by how many oxygens we have are 3 equals to minus 1. Let me write it in a neat way. Plus 3 minus 2 equals to minus 1. This means that X plus simple math, then we're just doing simple math, is equals to minus 6 is equals to minus 1. This means that X is equals to plus 4. Plus 5, sorry. This is how we are able to calculate the oxidation number of chemical species. We have to bear in mind that oxygen, usually minus 2, only in H2O2, the oxygen is equals to minus 1, the oxidation number of oxygen. Hydrogen is usually plus 1, and then we can solve to calculate the oxidation numbers of a chemical species. Now, the last thing I want to discuss in this video is what do we mean by oxidation number? How can we use the oxidation number? Now, oxidation number, as I've mentioned before, is so that we can track the electrons if are being lost or gained by chemical species. So we need to look at the end of the day to the redox reaction. In an oxidation and reduction reaction, there is a change in oxidation numbers of atoms involved. So there must be a change in the redox reaction there must be a change in oxidation numbers in the chemical species that are being involved inside the redox reaction. So in oxidation, the chemical species usually loses electrons, but there is an increase in oxidation number. It increases the oxidation number. In oxidation, there is an increase in oxidation number of an atom. And in reduction, there is a decrease in oxidation number of an atom. This is the two rules that we should bear in mind. Whenever the oxidation number increases, this means that it's oxidation. Whenever the oxidation number decreases, this means that it's reduction. Let's have a redox reaction, which is the combustion of carbon. Here we have oxygen is equals to 0, monoatomic. Carbon is equals to 0, the oxidation number of carbon is equal to 0, the oxidation number of oxygen is also equals to 0, also monoatomic. Here, the oxidation number is here, let's talk about CO2. Now, oxygen here is equals to -2, and I want to solve for x minus 2 times 2 is equals to 0, so x is equals to 4. So here the carbon is equals to 4, the oxygen is equals to -2. So the carbon was 0, it becomes what? It becomes 4. Here the oxygen was 0 as well, and it becomes -2. The carbon oxidation number here increases. The oxidation number here increases from 0 to 4. This means that the carbon undergoes oxidation. And here the oxidation number decreases. This means that the oxygen undergoes reduction. It gained electrons. Now, if you would ask me, is this a redox reaction or not? I would say definitely yes. This is a redox reaction because we have an oxidation we have oxidation half reaction, we have reduction half reaction. So this is definitely a redox reaction. Now, this is what we mean by the change of oxidation numbers. One chemical species, the oxidation number should increase in it. One chemical species, the oxidation number should decrease in it, so that we can say that this is a redox reaction. Let's talk about more complex reactions. So here we have Al is equals to 0, Fe2O3. I need to solve for Fe2O3. Fe2 was 2x, I don't know, plus -2 times 3. This is a neutral atom, so equals to 0. So 2x plus -6 is equals to 0. This means that x is equals to 3. Right here, x is equals to 3. Oxygen -2. Let's solve for Al2O3. Al2 here becomes 3, and here O3 remains -2. The oxygen, I mean not O3, I mean the oxygen in the one oxygen in Al2O3, oxidation number of it is equals to -2. And then here we have the Fe is equals to 0. So is this a redox? Let's see. In Al it was 0, then it becomes 3. This means that the oxidation number increases. This means that it undergoes oxidation. In Fe it was 3, and then it becomes 0. This means that the oxidation number decreases. This means that the chemical species is undergoing reduction. So that this reaction is redox reaction. Why is redox? Because we have both oxidation and reduction half reactions are being involved inside this reaction. Okay, and now we were able to track that the Al is undergoing oxidation, Al is losing electrons, Fe is undergoing reduction, Fe is gaining electrons. Through the concept of the oxidation numbers, we were able to guess which element is gaining and which element is losing, and that's why the oxidation numbers are important in order to identify if the reaction is redox or not. Hope that you enjoyed the video, and catch up with you later with more videos. Thank you for watching.